Good afternoon, everyone. I'm Razi Izadi. I have a PhD in mechanical engineering, and I'm an assistant professor in Sapienza University of Rome and a visiting researcher in University of Bologna. Today, I would like to present to you a work on fracture properties of nanofibrous network using a hierarchical method that integrates molecular dynamics and peridynamics approach. Polymer nanofibers with diameters less than 100 nanometer have received increasing attention due to their unique properties. Fibrous mats or membranes are one of the popular structures that are composed of polymer nanofibers, and they are ideal for various applications such as tissue engineering, drug delivery, wound dressing, filtration, sensors, as well as capacitors. Among PNFs, or polymer nanofibers, special attention is given to the ones that are constructed from polylactic acid, or PLA. Because of its biodegradability and non-toxicity, it already exists in human body and it's approved by FDA for the manufacturing of bioresorbable surgical implants. And the PLA is an ideal candidate for loading drug molecules or mimicking extracellular matrix for tissue engineering scaffolds. However, PLA lacks antibacterial properties, and the PLA fibrous networks may cause infections, and they also need to be improved mechanically. One way to overcome these limitations is surface coating. For example, by doping polylactic acid with silver nanoparticles, it will give the fibrous network antibacterial features. It will improve the mechanical properties as well as some properties like conductivity, chemical stability, and therefore they become more ideal for applications like biomedical applications or food packaging. Nanofibrous network, however, has some complexities in their geometrical structures. They have multi-scale features, and they can have variability in their material properties. These features make it difficult to predict the mechanical properties of these structures properly. With atomistic simulation, we can provide deep insight into the mechanical behavior of these fibrous networks. However, the problem is that when the size of the system increases, severe computational expenses are imposed on the problem. A solution to overcome this limitation is to use multi-scale methods. In this figure, you can see the multi-scale methods that bridges between different scales of simulation. In a hierarchical multi-scale method, we will use the data that we observe at the lower scale and then transfer it to the higher scale. In this way, we can preserve the accuracy at the lower scale while we use the efficiency of the higher scale techniques. In this work, we present a multi-scale approach that it bridges atomistic simulation to macroscale description to study fracture properties of three-dimensional nanofibrous network. At the atomistic scale, we use all-atomolecular dynamic simulation on individual fibers, polymer fibers, both the untreated bonds and silver-doped ones. And at the higher scale, we use peridynamics to find the fracture toughness, to find the crack propagation, and the fracture properties. At the lower scale, as we said, we use molecular dynamics simulation. Of course, MD has a lot of detail, but long story short, by solving the classical Newtonian equation of motion for each atom, we can track the position and velocity of the atoms as time passes, and further using the principles and relation of statistical mechanics, we can extract the macroscopic and physical parameters. And the upper scale, we use peridynamics. It's a non-local reformulation of classical continuum mechanics. It's based on integral differential equation. A PD model deals with integral equation rather than spatial differentiation. Therefore, it is valid when we deal with this discontinuous displacement, such as cracks. And we use the bond-based version of the peridynamic theory, in which each material point in the body interacts through a bond with its neighbor points, with a finite neighborhood that is called horizon. For bond-based PD, there are two material parameters that play the role of constitutive parameters. C is the micromodulus. It represents the bond elastic stiffness, and S0 is the critical stretch. That's when a bond stretches. Beyond this value, it is considered broken, and the force in that becomes null. And these two material parameters are going to be determined from these equations and from the MD simulations. Now, if we go back to the MD simulation, to construct PLA nanofibers after equilibrium of the cuboid simulation box that you see at the left side of the page, we increase the dimension of the box 5 to 7 times the cutoff radius in the X and Y direction without rescaling atom coordinates in the Z direction. Consequently, the polymer atoms will not interact with their images in the X and Y transverse direction. In this case, without altering the periodicity of the simulation box, through a further equilibration, we obtain a nanofiber that is isolated in the lateral direction, but it has infinite length in the Z direction due to the periodicity in the Z direction. And from the stress-strain curve and the strain energy that is obtained from the deformation, we can obtain the mechanical parameters that we need to inform the PD. The two mechanical parameters that are required in the PMB model, this version of the peridynamics that we have used, are the bulk modulus and the energy release rate. The bulk modulus is related to the Young's modulus and the Poisson's ratio. The Young modulus is determined from the slope of the linear part of the elastic regime, and the Poisson's ratio we determine it from with using the radial deformation in the elastic regime when the polymer is stretched. And to find the critical energy release rate, we focused on the energy density during deformation. As you can see, prior to crack initiation, all the work done on the nanofiber is stored in the fiber as a strain energy that is associated with the external work. But as the crack starts to propagate and starts to grow, a growing difference arises between the external work and the strain energy that is related to the energy release rate due to crack propagation. The energy release rate equals the difference between these two parameters at these 2 points divided by the change in the crack area. A quick conclusion from the MD can be obtained when we compare the untreated and treated and doped and treated fibers. The integrity of the nanofiber is maintained in the presence of the nanoparticles, whereas the untreated nanofiber is completely detached at the same strength. And also the nanoparticle reduces the local atomic strain, thus it reduces the shrinkage of the cross-section and it prevents the local buckling. And doping nanoparticle quantitatively increase the critical energy release rate and it's avoid crack propagation. And to ensure that a correct transition from MD to PD is obtained, we simulated a single nanofiber in peridynamic and tried to match the ultimate force for a single fiber in PD with that one in MD. To this end, we calibrated the value of the horizon. Okay, so with calibrating the value of horizon, we ensure that the ultimate force in these two descriptions are the same. This is actually a good part related to this study, because in analogous study, either no convergence between the ultimate forces are achieved, or the main parameters that are obtained from MD are artificially changed to seek this convergence. Okay. Then, to prepare the point-wise configuration required for the PD, the fibers are discretized into evenly distributed points with lattice spacing here 5 micrometer. And for example, for the random fibrous network, we consider a cuboid, and a specific number of fibers pass through each pair of the planes of the cuboid. And the coordinates for the aligned fibrous networks were generated with the fibers aligned in the Y direction. And in also the figures, you can see the discretized version and the SEM images for PLA fibrous networks with both random and aligned configurations. And we use the maximum stress from the tensile test on the pre-cracked specimen to calculate the critical stress intensity factor, which is also called fracture toughness. To apply the deformation, velocities of 1 micrometer over a microsecond is applied over a strip of 50 micrometer on horizontal edges with an initial linear velocity distribution along the Y direction to prevent shocks. And to find the fracture toughness related to mode 2 or the shear mode, the tensile load is applied on a plate with inclined crack at the angle beta. That creates a mixed mode condition. Here we can see the plots of the stress-strain curves for random and aligned PLA fibrous networks, and the values that are obtained, such as Young modulus, tensile strength, fracture toughnesses at both modes. And a comparison of these values with available data, experimental data in literature, shows that reasonable estimation are provided by the method. Also in this figure, you could see the crack evolution and damage patterns in aligned and random pre-cracked fibrous networks, where the colors represent the damage value parameters. You can see that the aligned fibrous network exhibits slightly higher stiffness and Young's modulus. That is, again, consistent with experiments of Lopresti et al. However, as you see, the crack starts earlier in the aligned fibrous network than the random one. And also, well, in the random fibrous network, the crack doesn't grow in a straight direction, perpendicular to the loading direction, but the presence of different fibers in different direction deviates the crack path. Also, we can see that the effect of surface treatments. We see that it slightly reduces the Young's modulus. It's in line with experimental, again, observation. And its main effect happens after the crack initiation, when they decrease crack growth and they increase the elongation at break. The interesting point here is that this dominant effect of nanoparticles on the crack growth is observed both in MD and PD. So it may suggest that this method can preserve the physical properties of the material during this hierarchical transfer. And these are the publications that are related to the current topic, and I will be glad to discuss about each aspect of the work if you like. And thank you so much for your time and for your attention.